So in 19.3, we're going to study the idea of power consumption, but specifically electric power. We talked earlier this year about mechanical power, and we defined the power done by something as the rate at which work is done. Okay, so we talked about that earlier in the year as mechanical power. And we've already talked about things like generators and batteries that convert energy into electrical energy from whether it be mechanical or chemical. So here we're going to see how electrical power is consumed. Now, the idea is still the same though. We're looking at the rate at which energy is changed. So in this case, we're going to first talk about power energy rate conversions, and then we're going to talk about power and its cost. Okay, let's go through this quick cycle here. And what I'd like you to do is, as somebody reads this, I'm going to follow along the diagram and watch where I'm following along. All right, so Jake, you want it?
Yeah.
Nice and loud and nice and slow, Jake. Go ahead.
A charge will move from a higher electric potential to a lower electric potential, just as we've seen with an object falling from the sky to the ground. Should I read the parentheses?
That's okay.
At the battery terminal, the potential energy is high, and when it moves from B to C, the energy is converted into internal energy.
All right, so let's pause right there. This is where it's being converted. So it's got a lot of potential energy in the beginning. Those things we called charge carriers yesterday, we think of as electrons, have a lot of potential energy when they leave the battery. They hit the light bulb. That potential energy is used up and converted into internal energy, given off as light. That's the energy being used up. So at point C now, take a look at point C. After it goes through the light bulb, it has no potential energy. Keep going, Jake.
When the filament warms up. When the charge returns to point D, the battery then does work on it from point D to A, and as a result increases the electric potential energy by the same amount of chemical potential energy lost by the battery.
Okay, so what's happening physically, the charge carrier has potential energy, it leaves the terminal, it hits the light bulb. While going through the light bulb, the energy that the charge carrier has is converted into electrical energy, given off as light. It then has no energy from C to D getting back to the terminal. So look at A and look at D. Look at A and look at D. That's what a potential difference is. Remember from yesterday we talked about voltage being the potential difference. The potential at A is very high. The potential at D is very low. This is a potential difference, also known as voltage. Okay, so then we go from D, the charge carrier gets back into the battery. It gains energy from the chemical energy that's in the battery. It gains that much energy, raising it back up to where it started, and going through the cycle again, and continuously doing this over and over and over. Okay, so that's physically what's happening when energy is being used. It's important to know how energy is used and to understand it, because energy and power are very different things. What do you think of when you hear the word power? What do you think of? Strength. Okay, agreed. I hear strength. What else? Yeah, you say the power's out, right? Like electrical power, the power's out. What about when you get a bill? The bill you get, if you live in the suburbs, you would know this in your own house. The bill that you get is called a power bill or an electric bill. But it usually comes from a power company. And it's a little bit misleading because really, the company is not measuring power, but they're measuring the amount of energy that you use. But the rate at which an appliance uses energy is what power is defined as. So for example, a light bulb. How many watts are usually on a light bulb? Anybody know? What's the power consumption of a light bulb? Standard light bulb. Yeah, 60 watts. Some are 40, but mainly 60. Regular incandescent bulbs. Nothing with like the newer ones and stuff, they're a little bit different. So 60 watts. That's the amount of power that light bulb uses. It's not the amount of energy used by the bulb. They're different things. So power is the rate at which energy is used. Okay? It's like the change in the amount of energy being used by that. Now, if we think about this, we're not being billed for power. We're being billed for energy. So a month goes by. Guys, if you can't leave quietly, I'm going to get really upset. Let's go. Good luck in your match, okay? Do well. Kick their butts, please. If we think about what the power company is actually billing us for, they're billing us for a month's worth of energy. So if you have a TV left on for 3 hours versus one light bulb left on for 3 hours, they use different amount of energy. Okay, they're both occurring for 3 hours, but the power consumption of a TV might be like 1,000 watts. The power consumption of a light bulb is like 60 watts. So there's a lot more power being used by that TV. As a result, a lot more energy usage. Power and energy are related. So let's start with the relationship between power and energy. Again, is defined, even though it's defined similarly as mechanical power, it's defined the rate at which charge carriers lose potential energy. Okay, lose potential energy. So if we were to write this out, we'd say power equals the change in the charge carrier's potential energy over what variable for rate? What do you put it over when you're looking at a rate always? Time. It's always over time when we're looking at a rate. So this would be the formula for electric power. Now, it's not a formula that we're going to use because it doesn't involve voltage and resistance and all those electrical components. But this is what electrical power really is. Just like, and if you recall from earlier in the year, mechanical power was work over time, or the change in energy over time. This was mechanical power from earlier in the year. It's the same thing. Okay, but now we're specifically looking at the change in potential energy of those charge carriers. All right. Now, later in this section, we're going to look at the cost of leaving an appliance on. So before we get to the next formula, let's take a look and think about this formula right here. P equals delta E over time. Let's look at that formula. If I want to know the amount of energy that an appliance uses, and I know the power consumption of that appliance, and I know how long it's been on for, I can solve for the energy used, delta E. So solve this one for delta E.
Does it matter like how high, or like if your lights like dim, is it just the same amount, like you'll still charge you for it being on, or is it like?
It's a different amount of power used for dim lights.
So like it wouldn't charge as much, or it would still be the same?
It would charge you, you would be cost less money. You would be charged less money for sure if it's on dimmer.
Or if like an air conditioner, if it's on, like does it still matter?
Absolutely. That's why there's power save modes on it. When you turn the power save mode on, you'll hear it change. You hear the motor change, you hear a lot of things changing. It reduces the amount of power that it's consuming. And as a result, reduces the amount of energy. So power times time is really the change in energy. This is not given to you, but this is something that you are given in the form of this blue equation up here on your formula sheet for earlier in the year. So if you ever want to know how much energy is being used, and you have power and time, it's the product of power times time. Okay, always. A formula that's not given on your formula sheet, but you are given the ones in blue, so you should be able to come up with this formula if you need it. Okay, so put a little asterisk if you have to, and just write that down that you're not given this, but you need to understand where it comes from. All right, now, the formula that we're going to use for power comes from this, but it's not the same. And the derivation of this is in your textbook. I'm not going to go through it because it is time consuming and I'm on a budget for time today with the B-Day. So I'd like to just state it first. And the formula we're going to use is this. P equals IV. And that comes from this. And if you want to see where that comes from, look in your text on page 708 and 709. Okay, that's where it's actually located if you want to see. So this formula, current times voltage, is all we need to know what the power consumption is of an appliance or an electrical element. If you know the amount of current that's running through it, you know the voltage that's being drawn, you can figure out how much power that element or that electrical appliance actually utilizes. Okay, remembering that power is a rate. What is power measured in? Watts. Good memory. Watts. Okay, power is measured in watts. So, let's go ahead and look at an example. Actually, before we do that, let's look at how we can use this formula, the same formula, P equals IV, differently. What is the definition of voltage from Ohm's law? Yesterday, last night's homework. What formula did you use over and over again? Ohm's law, what does it say? Mike?
Was it the V over I? Or
Not V over I, but you're on the right track.
something like that. I don't really remember. Can I look?
Yeah, look real quick, go ahead.
Um,
Okay.
was it V over R equals I?
That works. Okay, that's one of the options. So let's use that first. V over R is equal to I. That's one of the manipulations of that formula, right? So if that's what I is equal to, put a V over R in for I right here. Okay, take this I, replace it with V over R. As a result, this becomes power equals V squared over R. This is another one of the formulas that we might use. And last but not least, if instead of replacing I with V over R, as we see right here, replacing this I with the V over R, what if we replace V right here, leave I alone, replace V with what the definition of V is? What's V defined as? IR. So let's go ahead and write that. And that becomes I times R, or simply I squared R. So these three formulas in boxes, the one in blue, the one in red, the one in black, all for power, are all the same formula, but they're all using different characteristics or characteristics of the element. Its resistance, the amount of current that's going through it, or the voltage across it. So depending on the problem, you might have to utilize 1, 2, or 3. Okay? Meaning the first one, the second one, or the third one. I think I gave you all 3 on the formula sheet. Somebody, you saw already? It's on there, all 3? If you don't mind, just check to make sure I did that, please. Okay, pull up the formula sheet and look in the section where power is. I think I gave you all 3 here. Okay, these are the 3 formulas that we just wrote down. Those 3. All right, but you should know, obviously, that by definition, power is the change in energy over time. That's something that we talked about earlier in the year, which is what gives us this formula right here. And we're going to need this 4th formula in the box when we're calculating the amount of energy used or the cost of energy. We're going to need to know that formula to figure out the amount of energy used. If you know how much power an appliance runs on, and you know how long you left it on for, you can get the amount of energy used. The units are going to be kind of funky though. They're not going to be in joules. Okay, and we'll see why. And the only reason I'm going to not convert to joules in this one scenario is because in real life, when you get an energy bill, the bill is not in joules. It's in something called kilowatt hours.
What does it say?
Energy used or cost of energy. Okay, we're going to use this formula if we want to know how much energy has been used or to know how much energy costs. So let's look at 2 examples of this. The first of which, we'll look at one where we're going to use one of these first 3 formulas up here. And then in the second example, we'll talk about power cost. So we've got a TV connected across a normal standard American outlet. The TV dissipates a little over 1,000 watts of energy, 1150 to be exact. And we know that it's in the form of some EM radiation and sound. So light and sound, light and sound. Calculate the actual resistance of this TV. Calculate the actual resistance of this TV. What would the resistance of this TV be? Let's figure it out. So we know, first, 120 volts. What does that designate? Voltage. Okay, when you see V, think of the variable V also. Voltage. The TV dissipates 1150 watts. And it says of what it is next, but when you hear watts, what do you think? Power. Okay, those are the 2 known quantities. The question is, How much resistance does this TV actually have? What is the internal resistance of it? So which of the three formulas are we going to use? There's three choices. Kira, what do you got? Good. V squared over R. Okay, this should be very simple math. You're only literally making the choice between those three formulas. Solve for R, switching P and R. Giving us R is equal to V squared over P, which is 120 squared over 1150. Making the resistance, what number? 12.5? All right. 12.5, what are my units? Yeah, what is that? Ohms. Ohms for this one. Okay, that symbol omega. And if you want to draw your omega, start at the bottom left. Just draw a line, a little half, or like an arc, and then another one. All right, that's the internal resistance of the actual TV. Now, let's look at an example that's a little more applicable, because we calculated the resistance of it, but unless you're an electronics person and building things, this is not really useful for everyday life. Okay, unless you're a gadget guy, you need to know what the resistance is on an element. Maybe you're like into RC cars, or you're into like building motors, then this would be important in electrical circuitry. But let's look at one that's more important for everyone. Think about electric power cost, and I already talked about this. When you get the bill, you're getting a bill, and the bill is in units of what are called kilowatt hours. Kilowatt hours. Now, how do I know that that's an energy form? So let's say I get my bill at the end of the month, and the bill tells me that I've used, I don't know, 200 kilowatt hours of energy. That's what the energy bill will say. It'll give you a certain amount of energy you use. Then on the next line, it'll tell you the cost. The cost. And the cost is usually given as a rate. So let's first start with the rate, and then we'll come up with the cost actually. Let's list our rate first. They'll tell you a rate. And they might say, let's say 25 cents per kilowatt hour. That would make your bill $50 that month. How did I get that? How do I get that? If it's 25 cents per kilowatt hour and you've used 200 kilowatt hours, how do I actually get the cost? Yeah, you multiply. Okay, cost is going to equal the amount of energy used times the rate. Is this something that's not, or actually I think I did put this on your formula sheet. Give a quick look at it and check for me, please. But I think I did actually put this on your formula sheet. Okay, but the amount of energy used is in kilowatt hours. The rate is in dollars per kilowatt hour, therefore giving you an answer of dollars. Kilowatt hour cancels, giving us 50, and the units of dollars are left behind. Okay, so in a month, if you use 200 kilowatt hours of energy, and it's a quarter per kilowatt hour, that's what you would end up getting charged. I know for the location that I live, the electric bill for the first 2 floors is always around like 100, anywhere between 80 and 150, but around like 120 on average. Okay, so this would be probably a lower amount of energy than what I would use. And to be honest, this is a higher rate. I think the rate in New York City is around like 20 cents per kilowatt hour. Now, if I wanted to understand where I'm getting this from, I have to analyze it. And that's the tough part. On your electric bill, it's easy to figure out. It says this many kilowatt hours. But on appliances, it just tells you the amount of power consumption, how many watts it uses. So let's look at this next example to see how this is going to work. If we know, like, for example, a TV uses this much power, and you leave it on for 3 hours, what's going to physically happen? Or you leave bulbs on for a certain amount of time. And I just changed this example a little bit. So if you downloaded these notes before today, it might look a little bit different. I altered these earlier today. Okay. So you accidentally leave home for the weekend. So for 3 days, imagine 3 full days, without turning off the lights in your bedroom. There are 5 bulbs running on the ceiling light fixture at a power level of 60 watts each. So imagine you ever buy one of those for your room where they have like 5 bulbs coming out, or a fixture at the ceiling with 5 bulbs in it. 60 watts each. If the electrical energy costs about 25 cents, a dollar sign kind of should be with that, 25 cents per kilowatt hour, what does it cost you while you're out? Okay? So you leave your light on for the weekend pretty much. What's your guess? What do you think? Give me a quick guess. I have no idea. I don't even imagine you have no idea what the number is. What do you think it would cost? One light on. How much?
$20.
$20.
No, I take it back. Maybe like $5.
$5. Nobody else has a guess? Come on.
20.
20?
It said 20, Josh.
21.
Lots of both
I
answers.
said 21.
I just
21.
said 21, Josh.
No, I said 7.
No, I didn't.
15.
8?
No,
15.
yeah.
$15?
It's like 3
12.
days, and it's one light.
$12.
Is it like
$12.
one singular one light? Or
It's a light fixture with 5 bulbs running at 60 watts.
5 bulbs, okay, I thought it was 1. But I'm still gonna lock my
I'm
answer
still gonna
at
say
5.
50?
That's a bit much down. Racking up your bill.
Think about it this way. Just give you a quick relative nature in this problem. A refrigerator runs all the time. Okay? And a refrigerator probably runs on like 600 watts.
I said $5, Jen.
Sit around 5. Lesia?
20.
$75? Okay.
But,
No, give a reasonable answer.
what? Like, I did the math.
Oh,
I think I did it. I mean, it might be wrong, but it was like 30 bucks.
it was how much?
But yeah, everyone's
Something you did wrong,
I
yeah.
know $5.
It's around there.
5.4.
30.
$5.40.
All right, let's go through this. Let's see what we get. So, you leave it on for 3 days. 3 days straight is how many hours? Yes, 3 times 24 is 72. Then we know there's 5 bulbs. Each of them run at 60 watts. So how much power are we really running at? How much?
180.
5 bulbs. 5 bulbs. 300. You did for 3 bulbs. Okay, yes? So we need to know, and here's the thing. The power consumption rate is given in kilowatt hours, right? Kilowatt hours. So this needs to be in kilowatts. Okay, so 72 hours, the fixture running at 0.3 kilowatts of power. Now, I cannot calculate the cost unless I have the energy consumption. This is not energy consumption. So that's where that other formula comes into play that I kept mentioning. So you have to look back and think about this formula right here. If I want the energy, solve for energy. Energy is power times time. So if I multiply this, energy is power times time. So 0.3 kilowatts times 72 hours gives me 21.6, and my units are just kilowatt hours. That's where a kilowatt hour comes from. The power consumption in kilowatts, the time in hours, the product of those two things gives you kilowatt hours of energy. Okay, you can actually see what this is in joules, but it would be a very, very large amount. Okay, we're talking about, for example, 1 kilowatt hour is 3.6 million joules. That's why it's not given in joules. Joules are a very small unit. Okay, so 1 kilowatt hour is 3.6 million joules. So this would be upwards of like 60 million joules. So you wouldn't give units of joules. That's the reason, really, I think personally, that we use kilowatt hours. It's more reasonable when you look at the power consumption that human beings make or have. All right, so that's the amount of energy used, 21.6 kilowatt hours. If I want the cost now, the cost equals what? What was the formula we wrote down in the last one? Energy times the rate. The amount of energy consumed is 21.6 kilowatt hours. The rate is only 25 cents an hour. So, per kilowatt hour. If you forget to write it as 0.25, and maybe you write it as 25, okay, then the number you're going to get is going to be a very large number. Okay, but it's actually 0.25, because we're looking at dollars. So, what do you get as an answer? I know some of you already got it. What do you get as an answer for the cost? Not 5,000.
No, $5,
Oh, $5. It's in the $5 range. $5.40. You should get exactly.
I didn't do the math.
Okay.
I already made the answer.
That was a good estimate. Okay, it was a good guess. Now, how do I know that the units are right? Kilowatt hour cancels with kilowatt hour, leaving behind dollars. Okay, so think about this, just, realistically, a light bulb uses very, very, very little energy, especially relative to something like a TV or a fridge or an air conditioner. Okay, so when you're leaving things running for a long time, especially major appliances, for days at a time, your bill is going to go up a lot. I had to yell at, I happen to live with a family member, so I had to yell at my family member recently because she always leaves the lights on. Always, always, always. And in a nice way, but explaining this, that because I pay the bills in the house that I live in. So the electric bill has been crazy for the last few months since my family member moved into the house. So unfortunately, this made me think of, this example here. Usually, the energy rate is a little bit cheaper than 25 cents an hour. I use that because it was an easy way to round. But it's usually in the numbers of 17 cents an hour, 18 cents per kilowatt hour, rather. But it depends on your location, okay? So New York City differs from Long Island, which differs from New Jersey and other states around the country. And this differs from other countries in general too, okay? Does it make sense the way to do this? Okay, so you need to know that you can use any of those three power formulas, all right, to calculate power. You need to know that the amount of energy used is power times time, which is right here in blue in the middle. And you need to know that when you're trying to find the cost, well, I think I put this on your formula sheet, you're using energy times the rate. Did anybody check to see, was that correct? Is that on your formula sheet? No, yes, maybe. Thank you, Paul. It is. Okay. Oh, thanks, Josh. Way to really chime in there. All right, so